Okay, this is going to be the last two cases of curved mirrors for the three-part curved mirrors little video presentation. As a reminder, if you want some kind of a version of these notes, just go to Friday, May 29th. This link here is not my notes, but it's a website that will take you to just some other animations and a lot of reading material that you can go through in order to figure out what's going on with these mirrors. So yeah, I'm going to move on. So the last two cases involve case 6, an object in infinite distance. Now case 6, I don't have an object on the screen with case 6. So case 6 is just a special case of case number 3. So case number 3, as a reminder, this is the screen that you had in video number 2. We had an object that was, beyond C, right? And as you move closer towards C, you get closer to case number 2, image is going to format C. Image is going to be larger. Well, in other words, it's going to be the same size as the object. But as you get closer to the mirror, the image moves further from the mirror. As you move the object further from the mirror, the image is going to get smaller and move closer to the mirror. So case number 6, object at an infinite distance, or an object at a great distance, we're talking about things that are really far away. So like the reflection of the moon in a mirror, or even just think of, without thinking of reflection, think of if you're on the highway and you see a massive semi-truck really, really far down the road. It'll look really small at first. You don't have to look up towards it. You don't have to do anything to move your head. You can just look straight and you can see the top of the semi and the bottom of the semi all in one line of sight. But if you're standing, say, right, let's just use this image guy here. Say this is the semi truck, say this is you. If you're standing right next to the bumper and I say, hey, look at the top of the semi, you actually have to tilt your head up and your eyes up to see the top of the semi because it's really close to you. But if you're really, really far away from the semi truck, you just have to look forward and you can see the top and the bottom. So as you move further and further and further away, a lot of these incident light rays are going to appear parallel. There's going to be so little difference between the angles that they make when you collide with the mirror that they're more or less going to appear parallel. When you're close to a mirror, for instance, they're definitely not going to appear parallel. This blue line is a different angle than that red line, which is a different angle than that green line, right, for the 3 rules. So if you move ridiculously far away, all of your light rays are going to appear parallel. So I'm going to assume that I have them all drawn in already. I'm going to assume that I have some kind of height for my object, but so that's going to be a light ray that's parallel principal axis going through my principal focus, because that is by definition rule number 1 for any light ray. Light ray number 2 and 3, if I'm really far away, this object is definitely going to appear as if I'm drawing a light ray that's going through the principal focus. Well, it's going to appear as if it's coming down the principal axis. And so if that's the case, light rays traveling down the principal axis, it's just going to reflect back down the principal axis. So even if I am trying to draw rule number 3, which I offset them a little bit off the principal axis, just so you can see the 2 different colors, I'm technically going through the principal focus, and so therefore I have to draw a line that's parallel to the principal axis. Well, that just means I'm reflecting the red line back down its original path, which also means I'm more or less overlapping with rule number 3, the green light ray. Any light ray that's traveling through the principal, through the center of curvature, is just going to reflect back down its original path. So really, I'm just having a whole bunch of intersecting light rays that are just going through each other, and all the reflected light rays are just going to collide and intersect at the principal focus. And that's what you'll see if you have an object that's at a ridiculously far distance away, which is often just called an infinite distance now. I know infinity is more of an idea than an actual tangible concept, but that's kind of how it's written down. If you don't like the word infinity or infinite, then just say an object at a great distance, and that's good enough. So in reality, basically most objects that are at an infinite, quote unquote, distance away, all the light rays are going to appear parallel as they travel towards the mirror. And so therefore they will reflect more or less parallel to the principal axis, and therefore they're all going to travel through the principal focus upon reflection. And so therefore we can just say that any light ray, if I zoom in, so I zoomed in a little bit, any light ray that's traveling parallel to the principal axis, even if I was able to get them slightly off the principal axis so that we can see a difference, they're all going to reflect. So I just drew 3 random light rays. They're all going to reflect to the principal focus. And so that's how I have it drawn in. So I don't often make this something mandatory that you have to write down in your notes. This is just a concept that you're going to have to kind of remember. Case 6 is just a special case number 3. And if you think of the characteristics of case number 3, we can more or less say that, okay, if all my light rays were above the principal axis, and then they're all going to reflect below, or at least at the principal axis, which is still going to be below where my light rays actually were. And so you can therefore just assume that my image is going to be inverted. And we see that when you look at planets through reflecting telescopes. Planets are technically upside down from the orientation that you were looking at them as. So often when you look at the moon or other planets, Jupiter, Mars, Venus, through a telescope, you're often looking at it upside down. Now, right side up and upside down in space are meaningless concepts because there is no right side up or upside down. So I'll just say it's upside down and compared to just looking straight at it, if we're talking about planets. So as far as image characteristics are concerned, again, if we're at an object at a great distance, it would have to be really large just for us to even have any kind of discernible image. Imagine trying to see an ant down the highway. You can't. You have to walk up and it has to be pretty close to you before you see an ant. So think of it that way. You can see a semi-truck ridiculously far away, sometimes a few kilometers away, and therefore it's large enough to actually have a reflection at a great distance. So try to think of it that way so I know, and when it does reflect into a mirror, it's going to have to fit in the mirror, so therefore it must be smaller, and so that's why we have image characteristics to be smaller. Attitude, we'll have to just assume it's inverted, again, basing that off case number 3. Location, it's going to be at the principal focus. Technically, it'd be like a micrometer or a nanometer off the principal focus, but that gets to the point where we're just splitting hairs and we just say, fine, it's at F. So location, it's at F. And technically, that would therefore make it a real image, even though that would be really hard to actually form an image. Now, when we do a lab on this, you guys actually find your principal focus by putting a little light bulb or a candle or some kind of bright object far away from mirror. It won't be an infinite distance, but it'll be far enough away from the mirror that you'll measure an image pretty close within a millimeter of where your principal focus is. And that's usually all a ruler can measure, is within an accuracy of a millimeter. And that's typically good enough for most cases, experimentally speaking. So that's case number 6. It's not in your actual notes. It's just an extra little thing. Case number 7 is the convex mirror. So when it comes to the concave mirror, there are 6 different possibilities. Convex mirror has one possibility for where an image is going to form. So therefore, there's only going to be one convex mirror. So therefore, case 7, convex mirror. It doesn't matter where I place my object, there. It doesn't matter where I place my object. The image is going to form in the same overall location. And I'm going to have the exact same image characteristics. So the convex mirror, you would probably recognize as those, I call them shoplifting mirrors, because if you look at any gas station, grocery store, convenience store, if you look up and you'll see, if you don't see cameras, you often see these mirrors. So these convex mirrors are really great for getting a wide field of view and giving you an image that's going to be smaller. It increases your field of view. Often you'll see these convex mirrors also on the side view mirrors of the big massive trucks. So you can, it takes away the blind spots. You can see a lot more. So that's essentially your convex mirror. So the reflecting surface is on this side where my mouse is, compared to your concave mirrors where the reflecting surface is on the cave-in side of the mirror. So again, with your convex mirror, your center of focus, your center of curvature and your principal focus are on the opposite side of the reflecting surface. So now I have my object over here. Let's get to the 3 rules. 3 rules basically say any incident ray traveling parallel to the principal axis. So same rules apply. Measure how high that is. My object is, I used 1 centimeter. tall or 10 millimeter tall object. So therefore I would just measure where that is on the actual mirror and just draw a straight line to it, make sure it's parallel, and it's supposed to reflect through the principal focus. Now, this is transmitting through the mirror, technically, if I follow this rule to the right to the T. We know that's not how reflection works. It's not going to transmit through. Reflection means I have to go back in the opposite direction. Maybe not directly the opposite. I have to follow the law of reflection, draw the normal line, angle of incidence equal angle of reflection. But again, when it comes to curved mirrors, we tend to not draw the normal lines. So it will reflect as if it came from the principal focus. So that's the whole idea of a diverging mirror. It's going to spread out to the image. So do make sure, though, that you keep this dotted line so that we have the path of the reflected ray. I don't care where the incident ray is going. If you feel like you want to draw a line that goes straight through and knock yourself out, probably mark it wrong. Ignore the dotted line for the incident ray. We're only concerned with what the reflected ray is doing at this point. Okay, so you have to actually translate that through, and it reflects as if it came from the principal focus upon reflection. All right, so we're still kind of following rule number 1. Rule number 2 says any light ray that's traveling through the principal focus. So again, when it's on the object side, it's a nice solid line. So I have a solid red line there for rule number 2, and it's aimed through the principal focus. You don't have to draw this dotted line right there. I often don't in my own notes, but this is where it was headed. So any light ray that's traveling through the principal focus should reflect parallel to the principal axis. So I just, again, you don't need that dotted line. That's just how it was aimed. And plus it creates confusion. So you don't have to draw that in. Just make sure your ruler is lined up with that principal focus like I have it there. And it should reflect parallel to the principal axis. So again, when you make it a parallel line, measure the height. So this height is 4 millimeters-ish. So I draw a 4 millimeter dot there and a 4 millimeter dot there, and then I draw my reflected light ray. So it's reflecting on the object side, as mirrors tend to do. The light ray is reflected on the object side. And as you can see, the actual reflected rays for rule number 1 and rule number 2 are not actually going to intersect on the object side. And so that is why we have to transcribe our reflected ray on the opposite side of the mirror. So I have an intersection between 2 reflected rays right about there. All right, so that's rule number 2. Okay. Rule number 3, still just draw one line. The line changes as you go from one side of the mirror to the other as far as whether it's solid or dotted, but rule number 3 is still the best one to draw because it's only one line. Any light ray that travels through the center of curvature is just going to reflect back down its original path. So you get your ruler involved, just draw a straight line connecting C with the top of the object. It should be dotted once you get on the other side of the mirror because there's actually no light on this side of the mirror. So it's just the path it was following. And then it just reflects down its original path. And so you just basically trace that line going the opposite direction. So I have an arrow pointing towards C and I've got an arrow reflecting away. Okay, and if you notice, all 3 light rays, the reflected light rays, the transcribed light rays onto this side here, collide at one single point, which is great. And so that's where I put my image, where all the reflected rays collide. And as you can see, the image is a little bit smaller. All right, we knew that right as soon as we measured this red parallel line that, hey, this one's going to be reflecting at a 4 millimeters from the principal axis. So that's usually a good indicator of how tall your image is going to be. And so therefore we know that the size is going to be smaller. So as far as image characteristics, we have a smaller image. Attitude, it's erect. So therefore it's right side up. And you'll notice, compare this to all the other cases. The only other case where it's right side up is case number 5. And that is also a case where the image is formed on the opposite side of the mirror. So the virtual side. So typically if you have a real image, it's going to be inverted. If you have a virtual image, it's going to be erect. So just something to kind of remember. All right, location, I could say it's beyond the mirror, but specifically when it comes to a convex mirror, it's going to form somewhere between F and V. All right, if I move this object closer, aside from how the light rays would probably change, the image is going to get closer to the mirror. If I move this object further away, the image is going to get further away. But even if I try to move this to an infinite distance, the furthest this guy is going to move away is your principal focus. All right, so rule number 6 would apply for the convex mirror as well. But by and large, you wouldn't use a convex mirror for an object at an infinite distance. So the image regardless of where this object is going to form somewhere between F and V on the other side of the mirror. So location between F and V. And again, because you're on the opposite side of the mirror, it's a virtual image. So that is all 7 cases of your curved mirrors. 6 cases for your concave mirror, 1 case for your convex mirror. So I don't have multiple cases for convex mirrors. This is going to be the only situation, right? Regardless of where this object is. Okay. So you can pause the screen if you want the summary. This would be something you'd more or less be expected to know, the image characteristics for all the individual cases. So again, these are all qualitative characteristics, whether that's larger, smaller, same size, whereabouts you're going to find the image compared to the object. So those are just things you should probably write down. Pause the screen or stop the video here and just write these all down. The rest of this video, I'm just going to explain some errors you might see in your work. Sometimes you have these things called spherical aberration. So a spherical aberration is when you have a perfectly circular or spherical, if you will, mirror. These don't make for great curved reflections in the sense that if it's too large and too perfectly round, you're going to create this aberration. In other words, blurry images, because contrary to what I told you, parallel light rays on a perfectly spherical mirror are not going to all collide through the principal focus. For that, you would need a parabolic mirror. So in other words, you'd either have to do one of 2 things, either pinch these 2 ends of the concave side down a little bit, and then it will change where the principal focus will be to slightly further inwards, or if you pull them up, in other words, think of taking both your hands, fingers there, and put your thumbs in the very center there and sort of pull it back and bend it out. So it'd be less curvature, if you will, almost straighter. You'd be moving your principal focus further away from the mirror. And in that case, when it's a lot more parabolic, you'll have light rays collide at just one principal focus if they're all parallel. But this is an issue with spherical aberration. You're not going to get a perfectly unblurred image. So in your homework, it might look like this. If I drew the mirror too round for you on your paper, or if I made it too large for you, you might have cases where even if you drew all your lines perfect, you drew all your lines parallel the way they're supposed to be drawn, you might end up with situations like this where you have intersecting light rays at way different points, right? So only 2 of them intersected at any given point. So in this case, the way I have this thing drawn, I purposely drew this. It was a perfectly spherical mirror, and I have spherical aberrations. Very often you'll notice that I kind of left a lot of these mirrors out. I would erase parts of this because that is one of the fixes for spherical aberration. You would just block out parts of the mirror. You don't want the mirror to be that good or to be that large. So often you will just want a very small section of a spherical mirror when you're trying to actually find out where an image forms. And that's one way of limiting spherical aberration. So you can either cut the mirror down or just black out the other parts of the mirror, so that way you won't get spherical aberrations. So that's one of the fixes. Here's just a quick little example. Yeah, typically you'll want to use a parabolic mirror if you want to have the clearest image possible. And so in your notes, your worksheets, for the most part, I gave you all parabolic mirrors. So you shouldn't see any spherical aberration, but that is an issue that does come up. If you want to see more, I'll put a link down below for examples of spherical aberration and what these blurry images look like in the description down below. But I think that is it for curved mirrors and some issues that could happen. So I'll end this here, and email me if you have any questions. The next video I make will be about the math and how you can actually find out where all these images are supposed to be, and you can mathematically show the image location and size and whatnot. So that's the next video.